algebraically, adding two vectors is really nice. If you have a vector with components a1, a2, and a vector b with components b1, b2, their sum has first component a1 plus b1 and second component a2 plus b2. So here's a short example of that. The geometric interpretation, so look, the arithmetic or the algebra surrounding vector addition is very easy, right? Just add component-wise, a vector plus a vector gives you a new vector. The geometric interpretation is a little harder, but the connection has to be made. If this is just a thing that's done algebraically without being understood geometrically, we don't really get to draw without drawing, right? The whole point is if we understand how each algebra thing connects to a geometry thing, and we know what happens in 2D, and let's say we convince ourselves, then where it's harder to draw in 3D, at least we can go back to the algebra. So what you should do, this is one geometric interpretation, is draw both vectors that are given to you, the summoned vectors, as position vectors. And then the two arrows drawn are two sides of a parallelogram. What you just need to do is complete the parallelogram. And then the result of a plus v is the vector that's the diagonal of the parallelogram, which starts at the origin. It just really actually works out. So check out the previous example geometrically. Let me actually click on the link. And yeah, so I've got this vector in red here. What is that? 8, 1 in angle brackets. And I've got this vector -2, 2 in angle brackets. And if those two vectors are thought of as edges of a parallelogram, then this is the complete parallelogram here. And then the vector that starts at the origin and happens to be a diagonal, so it has to not be one of the two red edges, but this diagonal right here. This point right there, right here, I guess, what is that, 6, 3 as a point? But then I'm talking about this arrow, so the vector in angle brackets would be 6, 3, close angle bracket. That vector is the sum of these two red vectors. And it really works, right? If you go back, take a look. Is this the same example? Oh, look at that. It is. This was perfect. This 6, 3, it really works, right? It's just if you want to call it that, you could just call it the coincidence of this algorithm for adding the vectors up here. It aligns coincidentally with this geometry. It's exactly what happens. That when you add the x-coordinate 8, or the first component 8, to the other vector's first component -2, and you get 6, you end up right here. That's where 6 is, right on the x-axis. And then same story for the y. So I hope what you're seeing here is, of course, drawing the picture in 2D space, it's not hard, because we have paper to draw on. But I hope that this picture makes sense. I hope you're convinced that the geometry and the arithmetic are connected. And the point being, this picture is, I guess, easy enough to picture in your mind in 3D vector world, but it's hard to actually draw. If you actually had to draw, it would be challenging, right? So when you at least add two vectors in 3D space, you can just imagine the drawing, but don't actually try to draw it because it's just painful. Right, so adding vectors in 3D space is exactly what you'd expect. The picture, let's refuse to draw. It's exactly what you'd expect. And then another key operation we just saw a vector plus vector equals vector. Now we need this thing called scalar multiplication. So we'll take a scalar, or a number, called c, and a vector. Notice the vector has an arrow above it. And the operation's real nice. I guess it looks like distributing. I would just shy away from calling it that. You just take the scalar c that you'd like to multiply by the vector, and that number c ends up in the result vector being multiplied by each of the components. So you see this small example here. The scalar 2 times the vector -6, 8 ends up being -12, 16. Real nice. Again, the arithmetic, not so bad. The geometric view is the thing we need to really focus on. What happens is you take the vector a that you start with and you stretch by a factor of that scalar. If that scalar is negative, stretch by its absolute value. And then if the scalar happened to be negative, you also flip the direction, just 180 degrees. So I would ask you to try this on your own to not extend the length of this video too long. Please explore in the app, go through the steps that are shown there.